In this session, we're going to talk about the idea of a half-life. For a chemical reaction, what is a half-life? For a chemical reaction, the half-life is the time that it takes for half of the molecules to react. So half-life has units of time. Because we're interested in the time when we have a particular concentration, half of the initial concentration, we see that half-life is a specific solution of the integrated rate law. For a first-order reaction, the half-life turns out to be independent of the initial concentration, and each half-life is an equal period of time. We can see that in this example here at the bottom, where to go from 1 molar to 0.5 molar solution takes 6 hours, and then to go in half again, 0.5 molar to 0.25 molar, that takes another 6 hours. And then to go to half again takes another 6 hours. And then to go from 0.125 in half to 0.0625 molar takes another 6 hours. So it's half of whatever the initial concentration was. And in the case of first order reactions, that always takes the same amount of time, but we'll see that for other reaction orders, the half-life is calculated differently. So what do I mean when I say that half-life is a specific solution to the integrated rate law? Well, here we will derive the half-life equation for a first-order reaction. You could do the same exercise for the other reactions, and I encourage you to do that. So we know that the integrated rate law for a first-order reaction is natural log of concentration at some time equals negative kT times the natural log of the initial concentration. So for T1/2, we're interested in the time at which the concentration equals 1/2 the initial concentration. Okay, and if the concentration equals 1/2 the initial concentration, we can substitute 1/2 the initial concentration into our integrated rate law for the concentration at time t. So now we have natural log of 1/2 of the initial concentration equals negative k, and now this is T1/2, just to label it to make it special, plus, this is plus, natural log of the initial concentration. Now our goal is to get T1/2 by itself, so we can see how T depends on concentration if we want to calculate the half-life. Okay, so to get T by itself, the first thing we'll do is subtract that natural log of initial concentration over to the other side. Now, maybe you remember from somewhere back in your math education that the natural log of x minus the natural log of y is the same as the natural log of x divided by y. So we're going to use that property here to look at this difference in natural logs. So this, if we rearrange this, we'll see that the natural log of 1/2 of initial concentration over initial concentration equals negative kT 1/2. What's convenient about doing this is that now we can get the concentrations to cancel out. So we have natural log of 1/2 equals negative k t 1/2. So to get t by itself, we'll now divide both sides by negative k. And so we get that T1/2 equals natural log of 1/2 divided by negative k. Now this is a little bit awkward to have that fraction in the numerator, so we're once again going to use a log rule that, if we have natural log of x over y, and the negative of that is the same as natural log of y over x. So if we sort of apply the negative, we reverse the fraction. And so that comes out as natural log of 2 over k. And so that's the final form of our equation. We see that T1/2 equals natural log of 2 over k. Natural log of 2 turns out is a number. If you put that in your calculator, you'll get that it's 0.693 divided by k. So the T1/2 will have time units, and k for a first order reaction has inverse time units. And whatever time unit you use for k will come out as the time unit for T1/2. And so like I said, you could do this again, do the same exercise, but for the other integrated rate laws, and you could derive T1/2 formulas for each order. So like we said, for a first order reaction, T1/2 equals ln2 over K. And that means that we see in this equation, the half-life does not depend on the initial concentration. It only depends on the value of K. And that's why each half-life is the same length. So for a first order reaction, each of the half-lives are the same. In this case, they're each about 7 minutes. For a second order reaction, if we calculate the half-life formula, we get that half-life is 1 over K times the initial concentration. So for a second order reaction, the half-life does depend on the initial concentration. And since the initial concentration changes as you go through the reaction, each successive half-life is different. In this particular case, each successive half-life is twice as long as the last one, because your concentration keeps going down, and here concentration is in the denominator. So the first half-life we see here is only about, call it 50 seconds. And then the second one is, so that'd be 50, is like, 75 seconds? And then, so, they keep getting longer as the reaction proceeds. For a zero order reaction, or zeroth order reaction, T1/2 equals the initial concentration divided by 2K. And once again, that just comes out of the math of substituting the concentration at time t equals 1/2 the initial concentration. And so once again, we see that the zero order reaction, the rate doesn't depend on concentration, but the half-life does depend on concentration. And we see that each successive half-life in this case is shorter than the last one. And again, that's just a sort of a true fact about zero order reactions. So now you try. Hydroxyurea is a medication that's used to treat sickle cell disease. Sickle cell disease is a genetic disorder that causes red blood cells to be shaped like a sickle or a crescent. The average T1/2 of hydroxyurea in the body in a cohort that was studied of 97 children who had sickle cell disease was 1.65 hours. If the reaction is first order, what is the value of the rate constant? So here, we want to know the rate constant. We're looking for K, and we have T1/2. So what relates those? The T1/2 formula. Now we need to choose the right T1/2 formula for our reaction order. So here in the problem, it tells us that the reaction is first order. So that means we'll apply the first order T1/2 formula, which we said is ln2 over K. And here we know T1/2 and we're looking for K. So we'll rearrange this equation by multiplying both sides by K and dividing both sides by T1/2. Okay, so that we end up that K equals natural log of 2 over T1/2. So to calculate K, we know that natural log of 2 is 0.693 divided by T1/2 we said is 1.65 hours. And so if we do the math, we find that K is 0.420 hours to the negative 1. So if we can measure the T1/2 by, for example, measuring the time it takes to get to half of the initial concentration, then we can find a rate constant. And once we have a rate constant in order, we can calculate the concentration at any time using the integrated rate law. We can also think about whether or not 1.65 hours is going to be a reasonable half-life for a drug used to treat sickle cell disease. We could read more about this, but my guess is that 1.65 hours is a little bit too short for half of the drug to have degraded. Another good example of reactions that are first order are radioactive decay reactions. And we often report the radioactivity of a particular isotope using its half-life. So about how long does it take for half of whatever you start with to decay? And since these reactions are usually first order, they follow the first order integrated rate law and therefore the first order half-life formula. But concentration is a little bit irrelevant in this case. So you'll see that when we're talking about radioactive decay, we often substitute concentration molarity to just N, which means number of atoms. So look out for that in your practice problems.